Hey guys, welcome to this little video on the spot info node and vectors with Lightwave. We're going to cover these two simple little topics, or reasonably simple little topics at least. Or more to the point, we're going to cover these slightly complicated topics perhaps in that attempt to simplify them, should I say. Now the main thrust of this little video is the spot info node itself, but to help make sense of it we're also going to be dealing with vectors, so I just want to help you understand those as well. Which kind of turns this into a double-edged tutorial. So let's take a little look at vectors. Okay, first of all, let's answer the question of exactly what a vector is. Just for those who don't know, we're going to use a simple 2D example here because it's easy, and I'm going to draw a very crappy graph there. And this graph, of course, has two axes, being it's two-dimensional, an x-axis and a y-axis. Awesome. And we're going to draw a little line. Okay, so this is a graph. You've all seen graphs before, and there you go. Basically, this line is a vector. Simple as that. Now, there are a couple of pieces of information in a vector, and you can think about it in a couple of different ways. For instance, you can look at the endpoint of the line here, which of course is an xy coordinate, and that is a vector, essentially, this xy coordinate. Okay, no problem there. But what the vector also has is it has a magnitude, which is the length of the line itself. Okay, I was just going to draw a little m there for magnitude. So in this case, this 2D vector, okay, you've got x, y, m, effectively. If you want to think of it that way, this isn't technically accurate, but it does help to break it down in your head. So the vector itself isn't just the coordinate, it's the coordinate and the magnitude. Now there's another way to think about a vector as well, and that's to think about it in terms of its angle, because of course here we have an origin, just like we have in a 3D software, and of course this vector is forming an angle from that origin. Well, there's another angle here, for instance, as well. So a vector can also represent a little angle. So you can think about it in a couple of different ways, or rather you can treat it in a couple of different ways to use it to get hold of different types of data. You can also, of course, in your 3D scene or 2D space like this, you can have multiple vectors going on, multiple lines. And of course there can be angles that exist between these vectors as well. So you can compare vectors to one another in the angle between them, in their relative angles to the origin, in their coordinates, and of course you can also compare their magnitudes. So bingo bango, there's vectors for you. Very nice. Now let's take a little look back at our spot info node. You'll see that these blue output points here, okay, these represent vector outputs. So the data that's going to come out of these ports are vectors. Of course we're in 3D space here, so rather than being an XY, as I had in Photoshop there, these are going to be XYZ coordinates. The principle is the same, it's just happening in 3D space rather than 2D space. We also see on our spot info here a couple of the data types that we have available, such as ray direction and ray length. Okay. Now the ray direction data port here is just delivering the XYZ coordinate of the vector, whereas the ray length, this would of course be if we were doing something with our spot info that was looking up information on a given ray, the ray length is therefore the magnitude. And so the ray output of our spot info node, the ray is a single vector, but we have access to two different pieces of data, both the coordinate and the magnitude separately from one another. If we're looking at things like the geometric normal, the smooth normal, or the normal, which are basically just all surface normals, then those are giving out a direction, which is basically the XYZ coordinate, the direction that the vector is pointing in. In Modeler, when you've got your polygons selected and you can see the normals sticking out like that, they're sticking out in a certain direction. They have a vector, or rather they are showing you the vector of the surface normal. Of course the magnitude here is unimportant because all you're looking at is which way the face of the polygon is pointing. You're looking at its normal direction, so of course there's no magnitude to deal with. So therefore, depending what you're doing with the spot info node, or rather which of the data pieces you're pulling from it, at least in this whole top section of the green and blue data types, you get a mix of either the vector direction, the magnitude, or the direction plus the magnitude contained within. Now, I know what some of you may be thinking. You may be thinking, okay, RH, that doesn't really help much. You haven't really explained an awful lot of the spot info node here, and I'm still clueless. Bear with me. We are getting there. Now, what I have in my scene here is I have a little ball. It's a happy little ball. It's very nice and sweet, and there you go. Now, what this ball has, of course, is a surface, this polygonal surface that defines the geometry itself. Now, the spot info is only really it only really makes any sense when we are talking in the sense of a polygonal surface like this, because of what a spot is. A spot basically is just a point on the surface. Just stick your finger against your face, there's a spot. Stick your finger against the wall, there's a spot on the wall. Stick your finger against your desk, there's a spot on your desk. A spot is this sort of abstract thing in a way, but it's also this very simple thing. It's just a position on something, a spot. Out, damned spot, etc. So, if we take a look at this first data member here, the object spot, that little output port is delivering information about the spots on the surface of this polygon sphere relative to the object center itself, or the object's pivot point, because it's in object space. We could also get information about the spots that are on this surface in world space by pulling the world spot data member. Hang on a second, some of you may be thinking, which spot on the surface are we talking about? If you stick your finger on your face or the wall or your desk, there is a specific defined spot. But how do I define the spot on this surface? I don't get it, you may be thinking. Well, here's the thing. When you're looking at object spot, world spot, what you're looking at is every possible spot on this surface. This isn't delivering information about any one particular spot of that geometric surface. It's delivering information about every single spot. Now, of course, in 3D, in Lightwave, things are broken down. We're used to dealing with points and polygons and edges and so on and so forth. And you can think of the spots in that way if you like. You could think of the object spot as delivering information about every single vertex of this ball, or every single polygon. If we're looking at it through the camera, and of course via a render, then you could be thinking about it in terms of every pixel that rendered image is made up of. So of course the higher the resolution that you've rendered at, the more effective spots there are. As I say, it's a little abstract, but once you get the basic idea that you're looking at every possible point on the surface, then it sort of starts to make a bit more sense. Now, of course, once you've got that idea in your head, and it does make sense, the question, of course, next comes, well, what the hell do I do with these spots? We are, of course, used to seeing the ZBrush displacement, where you pull out the normal information at a given spot, and you apply a displacement at that spot, and that will vary across the entire surface as defined by the UV map. In a case such as the ZBrush displacement, the idea of using the normal information, which is of course pulling the info of every normal at every spot on the entire surface, cross-referencing that with a UV mapped image and displacing by the amount that the pixel on the UV map image that covers a particular spot is defining, white, black, grey, etc., to displace in or out. That's nice and straightforward and simple, and there's a couple of tutorials on that, so I'm not going to cover that again. We're going to look at something slightly different to try and help give an idea of different ways in which you can use spot info outside of that just normal displacement sort of thing. So, what I've got here is I've popped open my surface editor, okay, and I've got the nodes on for the ball object here, just on its surface. So what we're going to do is we're going to use our spot info node to create some surfacing effects. We're going to start by using this first data member, the object spot. That spot is basically every point on this geometric surface And because it's a vector output, the blue port, the data that is coming out is the vector from the origin of the object to every point on the surface, okay, which is of course a direction, a vector, and a magnitude. If of course the ball were getting bigger and smaller, then the direction of each vector isn't changing, but the magnitude of each vector is changing. So, first things first, what I've added here is a null. So I've got a null and I've got my ball. Now, if I can get access to every spot on this surface, and that spot represents a vector, okay, then every point that comes out is going to be slightly different. It's going to be a whole bunch of different vectors, okay? And this null, which is a scene child, of course, if I bring over my scene editor here, you can see the null is a scene child. It's not parented to anything. The null itself also, when it gets moved about in space, has a vector from the world origin. Okay, so I've now got two vectors here. I've got the null's vector, and I've got the vectors of every spot on this surface. So, since I'm in surfacing here, you know, texture, surface, material, whatever the hell you want to call it, and since we know from our little Photoshop graph that I can compare vectors, then what I should be able to do, for instance, is I should be able to look up the vector of a spot on this surface, and I should be able to look up the vector of this null, and from determining the relationship between the two, I should be able to use this null to create surfacing effect on the ball. And as I move the null, I should be able to move that surfacing effect around. Remember, of course, in the old layers panel, you've got reference object, okay, that lets you have a texture referencing something. This is kind of similar to that, but with more control, or rather a more finite precision in how we can access that control. Okay, so I've got my object spot here, which is feeding out, you know, information about every spot on that surface. Great. I'm going to come down and add an item info node, and the item is going to be my null, of course, and that has a position, okay, which is going to be its local position as it relates to its parent, or should I say its parent relative position. It's also got a world position, so I could be looking at world if I wanted, but we're just going to stick with local parent coordinates here because it's nice and simple. So I've got, you know, its vector here, which is its position in space. I've got the positions of all of the points on this ball. Okay, now all I need to do is find a way to compare them. Now, we're not going to talk about vector math too much, but if you jump into good old Wikipedia and have a little poke around in Wikipedia in the math sections, you can dig up a wealth of information. The way that two vectors are commonly compared, or two of the most common tools for comparing vectors, are dot products and cross products. I'm going to use the dot product here, so I'm going to go to math, vector, dot. Happy days. Dot will compare two vectors and deliver a result, which is the comparison between them. Specifically, what a dot product is the dot product of two vectors is the cosine of the angle between the two vectors. Remember, back in Photoshop, we can look at the angle that exists between two vectors. Yeah, that's nice and simple to understand. What is cosine? Good grief, let's not get into a trigonometry tutorial. Look it up on Wikipedia. Doing so has the added advantage of allowing you to go to Wikipedia and actually read information that is correct, which is something of a new experience for those of us who spend time on Wikipedia finding accurate information on there. But anyway, all kidding aside. So, I've got my vector which represents the position of the null. I'm going to plug that into A. I'm going to take the object spot, I'm going to plug that into B. So that's every spot on the surface and the position of this null, and their vectors are currently being compared to one another in a dot product sense. And I'm getting a result out here, which is the cosine of the angle that exists between those two vectors. Cosine is a value between 0 and 1, and that's why the output on the dot product here is a little green port, a scalar. Actually, cosine doesn't have to exist between 0 and 1. It can be, anywhere in the range of normal numbers. For the most part, it exists between 0 and 1. Okay, that's a green port, so I should really plug it into a green port, but that doesn't really make an awful lot of sense. Let's try it. Let's just plug it into luminosity. And we can see that we're getting an effect there already. And what I'm going to do is I'm going to switch my viewport to VPR, because this will help me see what's going on. I'm also going to turn on my GL overlay so as I can see my null here. And oh, look at this, straight away we can see that as I'm moving my null, I'm altering the luminosity of the surface. Cool, huh? Okay, right, it's kind of good fun. That's pretty cool. You can see that what we're doing, or what the node editor is doing, is it's taking the vector of this null, it's taking the vector of every spot on the surface of this object. I'll just switch to the perspective view there. And so you can see that all of the spots which are facing toward the null are being lit up and made luminous, and those which are facing away are dark and not luminous. So that's fascinating, really, isn't it? Yes, it is. We've got a surface effect which is being controlled by this null. That's very cool. So that's an example of something that we can get using the spot info node in surfacing. Now, it doesn't stop there. What I'm just going to do quickly is I'm going to grab my light. I'm just going to set it to 0%. And I'm going to push my ambient to 100% here. As for this next little bit, because of course I've just plugged the scalar straight into the luminosity. But of course, often when we're doing something like this, what we're really going to want to be affecting is we're going to be wanting to affect the color of the surface or some such. So what I can do is I can add a gradient node. Okay, I can make this result here be the input of the gradient. Of course, as I said before, we're looking at cosine here, which under most circumstances varies between 0 and 1, so my gradient here is 0 to 1, or should I say cosine really goes from -1 to 1. But anyway, all of that nonsense aside, so I'm going to go from orange to a nice aqua blue. Isn't that pretty? Okay, so you can see that the gradient is taking effect here, and I'm just going to unhook the old luminosity there, and I'm going to plug this into color instead. And now we can see that what we're getting is, orange on one side and blue on the other side. Okay, so that's all, really good. It's not much different to what we had before. We've just added an extra node to allow us to control color, a fully variable thing with a gradient, rather than just a black-white alpha-like property such as luminosity, diffuse, specular, blah 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 blah. Now here's an interesting thing. I'm just going to set this to 0 on the Z there, so we're only looking at the XY plane of this null ball relationship. And actually I'm going to set the Y back to 0 as well. Okay. Now what we notice is we would think that this this gradient looks a little bit sharp. I mean, it's certainly a lot sharper than the transition that's defined in my gradient node here. And we would expect this to, not be quite so sharp. Maybe that's because of, the comparison between the angles or something else. But if we see what happens when I move my null away, okay, we see that the transition actually becomes sharper. And as the, oh God, where's my null gone? Let's bring it back again. As we move the null closer, the transition becomes less. And you see that as we start to move the null inside the object itself, then it blends out even more. If we were doing a surfacing effect like this, who knows what we could be doing? We could be changing, obviously I'm doing it here in surfacing. You might use this kind of node setup in, say, fiber effects. Maybe some of you remember the old Wall-E Sasquatch example of the grass, where you had the little helicopter going over the grassy field. And as the helicopter passed over, it caused the grass to splay apart, creating, a downwash type effect from this little helicopter. That was using a null reference. Don't forget that we have got in nodes, fiber effects, and you can of course also in the fiber effects interface you can texture things, and of course you can dump nodal information on there. So you might use a setup like this to produce that same little helicopter over grass effect to cause the grass to splay or something like that whenever this null passes overhead. Okay, but for the purposes of this surfacing, you see that we are getting this strange gradated behavior, and we don't really want that, because we want, no matter how far away this is, we want this, for instance, to stay exactly the same. We don't want the gradient to keep changing on us like this. Let's assume that we always want to have this nice smooth transition no matter how far away the null is, and all we're interested in is, the face direction, which way around, which side of the sphere our null is on. Now, the reason that we're getting this behavior of it softening as we come closer and sharpening as we come further away is because, of course, both of these vectors that we have pulled out here contain magnitude. They are x, y, z directions plus magnitude. Of course, what is happening when I move the null away, the magnitude of its vector is growing, but of course the surface, that the points on the surface, the object spots on the surface of the sphere, are not moving away from the sphere's center. And so the difference between the magnitude of this vector and the magnitude of the vector at each spot is getting greater. The difference between the two is getting greater. The difference is becoming more pronounced. And of course, if you're looking at a gradient, a more pronounced difference between one side and the other is a sharper transition. A less pronounced difference between one side and the other is a smoother transition. Here's a funny question. How can I get the XYZ direction of the vectors but without the magnitude? I don't want the magnitude, perhaps. I want to dump that piece of information. How can I get rid of it? Well, when we're dealing with vectors, many of you will have heard of normalizing a vector. And basically what normalizing does is it just takes the magnitude and just slaps it to 1. Doesn't matter whether the magnitude is below 1, above 1, it just clamps it down to 1. And if we look at math vector, we find that we have normalized node. So I'm going to grab that. I'm actually going to grab 2 of them here, and I'm going to normalize vector coming from the null. We now see, no matter how far away the null is from the surface, gradient does not change. It stays just as smooth. It's lovely. Now, obviously, the magnitude of the vectors to the spots on the sphere's surface from the origin, that's not changing at all. If it was being changed by deformation or bones or whatever the heck, then I could normalize that as well if I wanted. So I'd just be able to normalize that guy. Of course, in this sense, it doesn't make a huge amount of difference. It does make a difference, as you see instantly. The reason is because it had a magnitude value, but I've just now reset that to 1, and I'm now getting a fully smoothed out gradient here. So there you go, but that would also help out if you were, of course, deforming the object itself. Anyway, I think I'm drifting a little off track there, different options and possibilities, and it could be this way, it could be that way, blah blah blah. The point is that what this simple little demo shows us is what the spot info node is doing. I know that we've talked a lot about vectors and so forth here, basically because I needed to talk about vectors so as you would understand more about what was happening within this node network, seeing as we are using the vector data components here. Real demonstration that I'm trying to show to you all is what spot info is, and as you can see from this very simple setup, this very simple demonstration, is spot info basically means all of these different possible pieces of information about every single possible spot on the surface at the same time. there's a spot here, and here, and here, and here, and here, and here, and here, blah, 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 going on pretty much ad infinitum. But just to break it down, there's a spot here which has a vector from the surface, and by being compared to the vector of this null, I'm able to colour it using a gradient. Similarly, there are also spots over here being evaluated, and when we compare their spots to the vector of this null, we get a different result, and of course our gradient therefore delivers a different colour, and so on and so forth. So spot info, which is the thing I did really want to show here, really is evaluating all of these different types of data on every spot on the surface at the same time. That's the important thing to take away about the spot info node. So I hope that that helps to clarify or do something or other for you guys some way, or helps you to get a little more idea about what the spot info node is, what it does, what the kinds of data it is delivering is, and of course how you can use it in new and creative ways. There we go. Thank you very much, and ta-ta for now.